last time we looked at everything related to principal component analysis in theory. Now, when we apply it today, you will get everything in theory. The theory can sometimes be a little bit daunting, but it doesn't matter. Once you come to application, the most important thing is that you do this application in your project, your longest, your thesis as well. So I've given you all the notes. I'm basically going to read with you and run it with you so that it will become easier. And then you'll be asking questions as we keep going. So I want somebody to read the case study here, the introduction that I have on the screen. Can somebody please raise a hand and read the introduction? Yes, Carla.
Yes, good morning. Okay, so welcome to the practice case on PCA. In this project, we aim to generate and visualize the PCA for auto MPG dataset and extract insights. The auto MPG dataset is a classic dataset used in machine learning, statistics, and data analysis. It contains various characteristics of 1970 through to 1980s cars and is commonly used to teach. It's commonly used to teach feature engineering, correlation analysis, principal component analysis, PCA, regression modeling, clustering. Because the variables are highly correlated, this data set is perfect for PCA.
Thank you. So guys, let me ask you, which of these analyses are we about to do today? Which of these approaches are we about to do today? Feature engineering, correlation analysis, principal component analysis, regression analysis, clustering. Which ones do you think we are doing today, William?
Principal component analysis.
And?
Clustering.
Not exactly, but at some point in the second case, I brought clustering somewhere, but that's not the ultimate for this very auto case. Esther?
That is correlation.
Correlation, exactly. So we are going to use this data set to understand correlation, but more importantly, to understand PCA. Okay. So, question is, what is the nature of the data set? You all have the data set in CSV file. Please, don't you have it, or you have it? You have it?
Yes, please, we do.
I will not really open the data set because you'll see me, but you can open it where you are so that you can follow. I've used the data set multiple times. It is made up of miles per gallon, which determines the fuel efficiency of a particular car. But the data is a bit old. The data is looking at cars that are between 1970 all the way to 1982. When I highlight my sentences, do you see?
Yes.
Okay, good. Because I wanted to know where I am, where I'm talking from. So he uses that. Then you will know, so the miles per gallon, if you were doing a regression, have you done the regression in, the basic one, have you done it in statistics for business analytics? Because I'm teaching that. Or is today you're going to do it? Have you started regression?
No, sir.
No, sir.
So miles per gallon is like something you are using to determine other things. So you want to see factors that affect miles per gallon. And miles per gallon, but when you're doing principal component analysis, you just don't care whether it is a dependent variable or an independent variable. It's just a variable. Okay. And the essence is that you want to reduce these features from 8. As you can see, the variables are 8. But of course, one of the variables is called car name, the name of the car. And this variable is actually a categorical variable. So because it's a categorical variable, we are not going to consider it as a variable because it's meaningless, it's not unique. It's too unique. Therefore, we will normally drop it, only used for labeling graphs when the need arises. But other than that, we are looking at the cylinder of the car. That can affect the fuel efficiency. Okay. Why are we saying that? We are saying that because if you have more cylinders in the car, like a 12-cylinder car is, whoa, ha, 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 okay, it will give you more power. And that will mean that you will have a lower miles per gallon. Yeah, sometimes some people think that that is expensive, but that is not. The 12-cylinder car rather gives you more power and then reduces the fuel efficiency, the miles per gallon. Displacement is another variable. That is the size of the engine. Okay, if the engine is big, large displacement, it means that you have more power, and that means you use more fuel. And the displacement ranges between 70 to 450 cubic inches. And then you have the horsepower, the vroom, 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 vroom. Okay. It measures the power of the engine. And if the horsepower is very big, then it means that you are going to, use more power. Sometimes some of these horsepower variables are not there. So you have missing variables there. The weight of the car matters. You can imagine an articulator and then a Ferrari. So normally when the car is very heavy with a big weight, it will reduce the fuel efficiency. And then the acceleration, which is normally from 0 to 60 miles per hour. You can imagine, today we don't talk about 0 to 60 miles per hour, but this is an old kind of data set, and we talk about maximum of 60 miles per hour. So that's the time you take to speed. Okay, when you have more powerful engines, you accelerate faster, and then you have fewer seconds to use. And then finally, the model of the car, whether the car was manufactured in 1970 or 1982 or 1978. Of course, if the car is new, the efficiency of the fuel is clear. The fuel is very efficient. So this is the data set, and we are going to apply PCA. Why are we doing that? Well, the essence of the PCA here is to reduce, instead of the 7 numeric variables, the PCA can bring it down to 2 or 3 without loss of information. So it combines them and creates a name for that. And as long as 90% of the information in the data is inside the 2 components, we are done. Okay. As long as 90% of the information, or what we call the variance, is inside this 90%, is inside the 2 variables, which have been created from the 7, then we are sorted. When you also do principal components, it can help you remove multicollinearity. And when it comes to regression, you see that in regression, when there is a lot of multicollinearity, the predictors, or what you call the features, they become too correlated. And when they are too correlated, what I mean by too correlated is that they move together too much. They move together. For example, your left shoe and your right shoe are too correlated. In fact, they are perfectly correlated. But sometimes you don't want 2 things to be correlated. Because if they are correlated, then it means that you are not able to separate them and to know their respective effects on a particular variable, because they are doing the same thing. That's what it means. When 2 things are correlated, they are doing the same thing. For example, if a husband steals money from the office, there's no need to ask the wife, because the wife is more likely to support the husband. That is if the wife is like one of our ladies here. But if the wife is a very wicked wife, that one there, you shouldn't ask the wife. And then finally, this data is very good for visualization. Okay, you can use it to create scree plot, biplot, scatter plot, and all kinds of plots. So let's go and load the data. Okay. Now here, I've just given you a few information regarding the packages. I know you know it already, but if you don't know any package now, you can ask. Pandas. Okay. Pandas is very good for data manipulation. in Python. NumPy is used for mathematical operations like reshaping, converting arrays, vector matrices, and all of that. And PCA, as you know from last time, has it. Seaborn, beautiful graphs, top. Okay, you normally will add that to Matplot library, okay, and PyPlot. PyPlot are basically for drawing beautiful things, but Seaborn is good for correlation heat map. We shall do that today. It's also very good for PCA scatter plot. Okay. And when you are doing something we call TSNE, a T-distributed stochastic neighbor embedding, okay, you need a lot of beautiful visualizations, and Seaborn is good for that. As for scaling, we know it. We do some scaling. In fact, last time you can see that we converted the raw data to the actual data using the scaling called Z formula. So when you have the Z formula, you can use the Z formula to convert this X variable to a Z variable. And what you are doing is that you are standardizing. So even if some of them are 4,000, 5,000, 6,000, and some are 2, 6, 7, you know, the gap is so wide, but you bring all of them around 1. Okay, you bring all of them around 0. So you have most of the data now between, say, around, say, -2 to +2, which is really cool. You standardize it because kilograms and dollars and yards and gallons are different. And then this last command will actually work with the software itself. Now, I just want to, I know you've not been taught T-distributed stochastic neighbor embedding, okay? But you've been taught principal component analysis. But this stochastic neighbor embedding is very good. Principal component analysis looks more at linear dimensionality reduction, okay? Meaning that the variables are many, x1 up to xn. And then you decide to now reduce it to just x1 and x2. Okay, but you do that using perpendicular dimensions, okay? Using perpendicularity. And that is why we talk a lot about orthogonal, non-orthogonality. And so you are using lines. So everything is based on linear dimensionality reduction. But sometimes the relationship among the variables look more nonlinear. And when you have that kind of situation, it requires that you use the T-distributed stochastic neighbor embedding. That's it. Okay, so we import both of them also into the work. Sometimes your data has a lot of high dimensionality, not just 2 variables, but more variables. That's when TSNE is very, very good. It can discover the hidden patterns, the clusters, you know, give you beautiful scatter plots, and then use it to complement your PCA. Very good. So let's load the data auto. I want you all to run this data. And when you run it and you've properly run it, your number on the left will change. Run it. Please be part of this because you will do that as part of your assignment and as part of your, you know, test. So it's nice that you are doing what we are doing. Okay. If you have not been able to run it, you let me know. When you run it, it will load the data. We are simply calling it data. You can use any name, but you're simply calling it data. And this is possible through pandas. So that's why you have the PD. This can help you to look at the head of the data, the top 10 rows of the data. The top 10 rows of the data. Okay. But if you don't want the top 10 rows, let's go back here. I can load the data again. Let me load the data again. You see my number has changed from 12 to 42. Okay. I can change this and make it empty so that I will load only the first few rows of the data, the first 5 rows of the data. So you can see that this one just gives you the first 5 rows of it. And you can see that these are the names of the car. For example, Chevrolet Malibu is one of the cars. Okay. And by the way, if you want the tail, you just change this command. Okay. And you can actually create a cell. Just click plus here, and then you can now run this, change the head to tail. And that will give you the last 5 rows of the data. I just ran it. It will give you the last 5 rows. So that tells you that we have 398 observations. Remember that you always have to include a 0. So even though it goes from 1 to 397, 0 is packed. And these are the cars. And these are the cylinders, the displacement, horsepower, weight, acceleration, the year the car was made. So if you can see that some of these cars were made in 1970, some of them are made in 1982. Okay. So far, so good. Now, let's check some information about the data. Anytime you want to know some information about the data, you click data.info. Okay. It will tell you the number of entries. Just as you said, you can see that the data is 398 observations from 0 to 395 rows. And what are the columns? The first column is the MPG of the car. So when you go up, you see that that is the first column. Then the second column is also 398. Now watch the 398. It just tells you that all the variables are up to that. The moment one particular variable is not like that, it means that there is a problem. In other words, there is no entry. But please know that there can still be entry that is still missing value. We'll come back to that. And whether the data is a Boolean, is a float, is an integer, whether the data is numerical, categorical, string or anything, it will tell you, yeah, you get the information. So it just shows that 3 of the variables are float, 3 of the variables are integers, 3 of the variables are characters or objects. Cool. So what can we say? We've already said everything, to be honest. There are 398 observations, 8 columns. All the variables except horsepower and car name are of numeric type. Now here, horsepower, you can see that horsepower is object. Okay. And car name is object. That is what we mean by they are categorical. Okay. They are string. They are string. And then the horsepower must be numeric. As you can see, it's one of the variables, so it has to be numbers. I mean, if you hear the name, you don't see the horsepower here being non-numeric, being categorical. Everything looks numeric, but when you go through the entire data, some of them are not there. Well, you see that very soon. That's a point here. So that's why I said we'll explore this further. Okay, so far so good. If you are with me and it is so far so good, type Y. Type the letter Y. I mean so far so good. Type Y. If not, type no. If yes, you are good, type Y. If you are not good, type no. I'm seeing Y. Okay, good. Let's go. The next is data processing and EDA. These are preliminary work. You will do this work, you'll be marked as part of your thesis. So take note of that. So the first thing we want to know is, we want to check whether there is some unique variable for car name. Car name is one of the columns. You can see that. So the question is, a car name, is it unique? When we say is it unique, is it like every variable is different, every observation is different? Yeah. And so we decided to check. And then you can see that you run this command, okay? And then you notice that the column for car name is, first of all, we know it's a character, it's object. And it has a lot of unique entries, very, very different entries. And they will not add any value to our column, so you can remove the column. It basically means that if you have the names of people and you don't want, you even want to anonymize the names, so you remove that from the data. So we are going to drop it. Anytime you are dropping something from Python or PyCharm, you use this is a beautiful way of dropping. Watch it. I renamed the data as data 1, and then I created a full independent copy of the data, and I called it what? Data 1. Okay. So I keep the original data, in there. So I create a copy for data one. I keep that one, I keep it there. Then I come back and have what? A name again for the data. And this time I have dropped the car name from it. So I'll still continue to use the name data. But suppose one day I want the original one, I can go back to data one. Okay. So data one is untouched this stage. Anytime you need it. The reason is that sometimes you do several analysis, so you have to keep and hold some of the data. Okay, now let's go back to horsepower. Now that we have removed that. Yes, Angela.
Hello, Doc. Good morning.
Yes,
Please, can you kindly go over why we are dropping car name again? I didn't really get the
so
point.
car name is, as you can see in the column here, at the far right here, you see that it has Ford Mustang, VW pickup, Dodge Rampage, Ford Ranger, Chevy. It's like everything is different. That's the first one. Second, they are English letters. They are English letters. And one of the things these analysis don't like is where you are talking about English letters in the numeric data. So if you are not going to use it for specific graphics, then you should have to remove that column so that we can, because correlation analysis, if suppose you are doing correlation analysis, you wouldn't need car name. Because car name has got different things. It's categorical. It cannot be correlated with anything. It cannot be correlated with anything. That's why we are holding that out for now so that we can go ahead and do analysis. Does that make sense?
Yes, please. Thank you.
Valentina.
Okay, Doc. So I want to find out that if you create a copy of the original data, can we use the copy to continue the processing?
Okay,
And
when
then
you
use
create
the
a copy, the copy is still the original. But we now continue with the one we have been using called data and rather remove the car name from that. So the original now becomes the data one and the new one is still data. So which one are you talking about? The new one called data or the original one called data one?
Okay, so because we were using data from the beginning, I was thinking that the data one
What do you
is
mean?
the copy of
No.
data.
The reason why we rather create a copy from the data and then call it data one. And then that copy, we rather use it as original and then continue using this one, which has been reduced.
Okay.
Yeah, by the card. Because we want to still keep the name data.
Thank
Okay.
you.
All right. So now, when you come to the information here, you can now see that we are still going to use the data. Now, if I run this thing on this new data, okay, let me just show you the tail of this new data. Okay, just watch. You see the car name will no longer be there. Okay, let's do this. So I'm going to run this one, okay, and then drop it here. I've done that. Now let me create another cell and dump it here and show you the bottom of the new data. You see, car name is no longer here. Okay, it's been dropped, so that last column is not there. Yes, Upon.
Doc, so when I ran the job side, I got an error, but later I had to do data.columns to find out if it's not there, and I noticed it's not there. So I'm sure some will run and will get an error. So when you run data.columns, once the car name is not there, meaning it has already dropped it. But I don't know why I was getting an error when I was dropping it.
No problem. You sorted it. Let's move on. So the next thing we are going to do is, these are all preliminary. They are not even the substantive thing. We are going to check horsepower column. Why? Because we did mention that horsepower has some unfriendly name. Now, first of all, you might not think that horsepower has some unfriendly things there, unless you go through the entire data, because when we run it here and there, It looks like 130, 165, they are all fine. Okay, but as you go there, you see some variables are not there. We are going to see that pretty soon. So let's run this and then you see. So watch here. First of all, I have to check whether there are values other than the numbers in the horsepower column. Okay, so I command that I want you to create for horsepower. I just call it HP. Is there a digit? Is there a digit? Is there a digit inside that column? If the string is made of digit, then let's call it true. If it's not made of digit, let's call it false. Okay. In other words, you create a Boolean for that. And if you find that there is, I want you to print where there is no digit. Anywhere there is no value for horsepower, I want you to, let me see. And I run it. So this is it. And when you see it, for observation number 32, 126, 330, 330, 336, 354, and 374. Within these particular observations, you see, they are not here in the Bible. They are question marks. The values are not there. Horsepower values are not there. So we got to solve that first. So there are 6 observations where horsepower has a question mark. Horsepower is not there for those 6 observations. So what do you do? Such observations where horsepower is not there, we call them missing values. And I promise you, you can't deal with missing values in many of our work. Okay, in many variables, you can't. You have to remove them or you got to replace them. So we are going to impute these missing values. Watch the word, impute, and change the data type of horsepower column. Because right now, the data type of horsepower column, if you go here, you see it, you spotted that. Horsepower here is object. But horsepower is not supposed to be object. It's supposed to be a float or an integer. And the reason why it's an object is because there are some missing values. So we're going to fill in that. Okay. Let's replace that. How do we replace that? We want to replace that with NP none. Okay. In other words, we are going to let whoever is looking at horsepower column to know that they are not available. Okay. If it's not available, just tell me it's not available. That's the point. But the data is not telling us that it's not available. So we are going to just institute this. Because with many machine learning algorithms, and even whenever you are doing normal mean, median, kurtosis, scaling, PCA, all of that, they don't work with string variables inside numeric columns. So if we have to replace the question mark with NP none, it would turn them into real missing values. In other words, right now, the question mark doesn't speak to Python that this is a missing value. But when you use the NP none, it tells Python, oh, okay. You mean these are missing values? Okay, I'll treat it like that. So we're going to do that, replace it with that, run this command, and you see that wherever those observations are, now they'll be replaced with NAN. Now, Python knows that, oh, so these ones are not there. Okay. It treats them still as a real missing values. Okay. I'm giving some reasons why we do that before you ask me. The columns contains missing values. Principal component and scaling cannot handle missing values. So before we do the PCA, we need to scale. So first of all, if you look at this column here, we still cannot run that. We know that is a missing value, but we still can't run the analysis. You know what some people do? They'll take this one and remove all of that column, everything I've highlighted from the data. What do you think that would do to your data set? What would that do to your data set? Anybody? Come on. What will that do? I take this row, I remove all of them from the data set. What would that do to the entire data set? Yes, Mapon.
Doc, it will reduce the total number of entries.
Good. From what?
Hold on.
From 398.
98.
Yes, please.
It will decline.
To what? -6 to what?
-6 will give us 392.
Good. So we will now have 392, but Do we normally want more things or less things? Yes, George.
We want less things.
Hey, where did you sleep tonight? Somebody should help my brother. In life, do you want more things or less things? Why are you doing
Less one thing.
More.
Generally, of course, I'm not talking about death. Good things is what I'm talking about. You know, you want more good things or less good things. So you want more air, more food, more money, okay, more life. So that is why it's not advisable to just be dropping all of this column because of one guy, horsepower. So what we are going to do is that we are going to replace it by the median. Okay. And you might be asking why the median. Anyway, so let's first replace it by the median. So here, I'm going to replace the question mark, which is now NaN. Okay, I do that. So this one will do that running. If it is not done, but in my case, it's done. Convert them to numeric type, which is a float, and then impute the missing values with median. So we'll look at that column, and then we'll pick the median to represent these values. Okay, and then we'll confirm whether now it is a float. I'm going to run that. Because if there's an error, you'll get that. Okay. You'll get this information, but this information is not an error. Okay. This information is just a warning, but it's still not an error. And again, you can go back and run the data to see. Okay. If we see, where is this one? Oh. Okay, it wasn't at this, it was at this particular ones. This one was to show. But when you go and check, you will notice that, okay, so you see the 32. You can just go back. Somebody is making noises here. Normally, I know that such people are not paying attention. No. I mean, it's obvious that when somebody is not paying attention, and you can see that you rather don't hear, you rather hear noises, so the person is not paying attention. In my class, if you don't pay attention, it will hurt you. So you can run the information here to see what is the situation. Okay. So now I'll just put something here, create a new listing, run this one. Just to get the information, I'll delete it. Okay, so you see that now horsepower is what? Is float. Okay, at first it was object, it's now float. And of course, we have removed the column called car name. So you can see that now we have 6 variables, including the 0. It's all good to go. We are all good to go. But the reason why we have to do the conversion and move from object to float is because the column was originally read as a string. Machine learning doesn't allow that. So float will ensure that it's a real number with decimals. Stop. Now we are ready to do the descriptive statistics. Now, for your statistics for business analytics this week, I lead that course and I've created a learning where you will do 4 things. If you haven't done, don't worry, your teacher is supposed to teach you 4 things. 1, contingency table. 2, descriptive statistics. 3, correlation. And 4, basic regression. So you're supposed to do that. So let's start with descriptive statistics. You can use this command and say, I want you to look at my data here and describe it for me. Okay. And I want you to transpose the columns so that the mean, the median, the mode, they don't come here. They don't normally come on the left. Okay. See, if I don't do that, if I don't include, let me run this in this. You see the way it is. You have the count here, rather. But I want the vertical section, the far left, rather to be on the numerator, on the top. Okay. So that's why I added transpose. When you add the transpose, it transposes and converts everything to that level. And that is how it works that way. Any question? Any question? Okay.
Hello, Doc.
Yep.
Hello, Doc, please, can you hear me?
Yes, loud and clear.
Okay. So when we scroll up a bit, it said that we are using a median because and it's the best if the data contains outliers. So my question is, how did we know the data contains that column contains outliers?
Where did I say that?
I think when we scroll up, a bit there was something at it. It said that median is the best choice when data has outliers. So I'm asking, how did we know we had outliers without performing any test on that particular column?
Oh, I'm only telling you that generally, as it is, median is useful when there are outliers. Now, I could use mean. I could use several other methods to be able to replace the thing. But I finished the work actually. I get your point. I've finished the work. I've run it already. I'll still show you very soon. I'll show you very soon. But I finished it already, and I knew that it has outliers. It has a couple of outliers, and that's why I decided to do it. But yes, you will run it, but I'm yet to run that with you right now.
Okay, thank you, Doc.
All right. So now you have this thing. This is a basic descriptive statistics, guys. I mean, this is easy peasy. Look at the mean. Look at the mean for MPG. It's just 23 miles per gallon. Okay? So it means that the average mileage is approximately 23 miles per gallon. Look at the mean for the cylinders. Okay, it's approximately 5.5, but let's say approximately 5 cylinders on average. Okay, so we are dealing with 5-cylinder cars on average. What about the displacement? Approximately 193 cubic inches, okay, is there with a smaller standard deviation. Sorry, no, with a reasonable number of standard deviation. Now, guys, let me tell you something. When you check every mean with a standard deviation, when the mean is smaller than the standard deviation, it means there's a lot of variation in the data. In other words, some of the data points are big, some of them are small. That's what it means. Some are big, some are small. Okay. So you can look at the means of every variable. For example, if you look at the year, you look at the year, model year here. Look at the lower number. The lower number is the minimum value, that is 70. The maximum value is 82. So it means that the years are from 1970 to 1982. It tells you the minimum value. And again, when you check the minimum values, every mean and every standard deviation, you will notice that the standard deviations are all smaller than the mean, which means that there is not much variability at all in the data set. So these are some of the things you can say regarding your descriptive statistics. Somebody said, why do you need to find descriptive statistics? Well, it can help you to know whether some of the variables have got different scales. For example, weight is in thousands. Miles per gallon is small. Look at the weight of a car. Okay. Look at the mean, the minimum value, 1,613. Look at the maximum value, 5,000. And then you check cylinders. Cylinder, the highest value is 8. So you can see that in terms of the variables, some of them have got huge values. So you've got to scale them. Some of them have got kilograms. Some have got cubic meters. Some have got other things. And that is why this is so. So now we can check some distributions. Guys, you guys are statistical people now. So let's look at a bit of distribution. Basically, we just want to know whether it's normally distributed, is not normally distributed, is left skewed, right skewed, And then those that are categorical, we also check their box plot. So look at it. This is for miles per gallon. Look at it very carefully. In fact, let's run it. So if you look at miles per gallon, you should run it also so that you know that there's a problem or not. So when you look at miles per gallon carefully, you will notice that it looks like it's right skewed. Look at it. It looks like the whole thing is smaller at the right side. That means it's right skewed. Okay. When you look at cylinders, if you look at 4-cylinder car, You can see the four-cylinder car, there are many of them which are four-cylinder cars. That is why the histogram for it is very, very, very long. So it means that many of them have got more four-cylinder cars. Okay. Now, which cylinders are not being used at all in this data? Which cylinders are very, very small in this data? Second.
No, the 3 and the 5.
Yep. William.
3, 5, and 7.
3, 5, and 7. Who is the West? That's what I mean.
7.
Yeah, that's all I need. Exactly. So you can see that majority of them are not using 7-cylinder cars at all. And the question is that, do we have that anyway? See the thing. We have that anyway. But anyway, that is what the data is basically showing. So you're able to get a feel of that. Now look at this one, displacement. What can you say about displacement in terms of normality and skewness? What can you say about displacement? You can see that it's also looking like, yeah, William.
I think it's not normally distributed. It's rightly skewed because
Moderately
majority.
rightly skewed compared to the previous one, isn't it?
Yes, please.
Moderately. What can you say about horsepower? Rightly skewed. What can you say about acceleration? Moderately rightly skewed. What can you say about acceleration? It's an interesting one. It appears to be a bit normally distributed, isn't it? It appears.
Yes, sir.
Yeah.
Yeah.
Don't attack me. I said it appears. Of course, the graph won't tell you everything. Now, this is exhibiting a lot of multimodality. Okay. Not normal. It's probably multi-normal. Okay. So that is it. Now look at the box plot on the right, because some of them, if you want to check the categoricals, look at it. What is that little dot or this little thing I have circled here? What is that? Yes,
Doc.
Outliers.
Outliers. Okay. So which of them don't contain any outliers at all? You should look at yours instead of looking at mine. Yes, Godfred.
The model year, the weight, the displacements, cylinders. Yeah, I think those four.
Yeah, some of them have got outliers, isn't it? Like horsepower.
Yes.
But honestly, if it has one or two outliers, it's not a wahala. It's not a problem at all. At all. So you can go ahead and then do your beautiful analysis on this. This is just to give you a picture of what's happening. I want you to look at cylinders. Just as the graph said, I decided to run to see the number of, you can see that 4 cylinders are having a lot of observations, which means most of the cars have 4 cylinders. And only 3 has got 5 cylinders. And as for 7 cylinders, they are not there at all. Now let's look at correlations. Let's look at correlations. What can you do? Now, you all have the code, but I will encourage you to go and fill this code because it took me time to just put it together. So first thing you do is that you have to ensure that it is going to be only on the numeric data. So if there's any categorical data, it should drop it. Okay? You don't want it to be with any category. So this will select only the numeric columns. Then you will generate the correlation on these numeric columns. You will also tell the system to give you the p-values. What do we mean by that p-values? P-values will tell you whether the correlations are significant or not significant. In case you don't know, let me just tell you. Whenever you have a p-value, and that p-value is less than 0.05, it means that whatever correlation you saw up there is significant. Whatever correlation you have calculated. So let's say you calculated a correlation which is 0.82. And the p-value for that correlation is 0.00001. Is 0.82 significant or not significant? Well, 0.82, will it be significant or not significant? What do you think? And I've given you the rule already. What would that be? William?
I think it will be significant because 0.0001 is lesser than 0.05.
Very good. So to mean that this particular correlation is significant, okay, that's what it means, that this particular correlation is significant. So 82% is significant because the p-value is small. Anyway, so that's what you're going to be doing here. You will calculate it, each correlation, and then bring in the p-values. This is really good than the original one that I knew about. So you can see that for each correlation, there is a correlation coefficient and there is also a p-value. So let's take, for example, one of them. So let's take this very one. You can see that the correlation between cylinders, let me get the next one. The correlation between cylinders, and so that's cylinders and weights. Okay. If you check the correlation between cylinders and weight, that gives you 0.9. And looking at the fact that the p-value is what? The p-value is actually 0. Okay. And because the p-value is 0, what does that tell you? It means that that particular correlation is significant. It is significant. It is highly significant. If you are a bit confused, let me know. So who can tell me the correlation between displacement and MPG? What can you say? Displacement and MPG. Displacement and MPG. Displacement and MPG. Displacement, remember I told you that the more you communicate here, the more you make me slow down. Yes, Goka.
Okay, so the correlation between displacements and MPG is minus 0.8, and then the p-value is 0.0, which is very significant.
Good. So you're able to generate quite a number of significant values. That's what it means, guys. You're able to generate quite a number of significant values. And you're able to tell whether it's significant or it's not significant. So that's it. That's correlation matrix. And you need this because principal component needs this kind of correlation to do. For you to combine two things, they must be correlated with each other before you can do. So this gives it, and not just being correlated, but they must be significantly correlated. Okay. They must be significantly correlated. And that is exactly what. Now, you can use the original one that came with this thing was this, but it's not beautiful. So that's why I created a video. And you can change the coloring anytime. So you can see that here I am using Inferno. So you can use Viridis, Inferno, Cool Warm, and several other CVDs and so forth. Okay. So let's look at some key information. The variable MPG has a strong negative correlation. Okay. The displacement, horsepower, and weight. You can see that. Horsepower and acceleration are negatively correlated. You can check it. The variables weight has a strong positive correlation with horsepower, displacement, and cylinders. So it means that these variables are likely to be combined, though. That's what it means. So let's look at it. Horsepower, displacement, and cylinders have a strong correlation with weight. Okay. So when you take weight here, okay, this is weight. This is a row for weight. Horsepower can be correlated with weight. So displacement, okay, look at the values. Look at the values. 0.9, 0.8. They are sharing some things in common. So clearly, that is telling you something. It's telling you something that those three may be combined, and you're going to see whether that is true when we come to the PCA. So basically, the correlation helps you to step up your game. Now that we know there's some sort of positive correlation, we can now proceed. You have to now, I'm running this. You have to now scale the data. We know about the power of scaling. In the theory, we dealt with scaling. Okay. Scaling is just converting the original X variable to a Z variable using the mean and the standard deviation. Now, this command will automatically do the scaling for you. It's called standard scaler. Standard scaler, this one. So you have it there. It will standardize the features, that is each column, by removing the mean and scaling it to the unit variance. When you look at this one, it takes the scale data. So the standard scaler will have this. Then come up here. You see, when we're dealing with the correlation, we kept the data as numeric. Now that we are dealing with scaling, we are going to rename data as well, scale data. Okay, so how do we scale the data? First, we fit transform the data. Okay, so the fit will calculate the mean and the standard deviation. That's what it will do. That is the mu and the sigma. Then the transform will apply the formula to the scale for each. So the transform will just do x minus the mu, and the standard deviation is already calculated to get what? The z. So the fit transform together will do both. And it will give you the z value for each of the things. So I did a thing, and now I want to show you the top part of this scale data. So this is data scaled. And you calculate MPG value is now within, it's not even more than -1. Okay, it's quite below -1. And then even the highest ones, like model year, okay, they are more, not even up to 2. So all of the data are kind of between -1 and +2, scaled. Beautiful. Okay. So now you've got your scale data. You can now proceed to do your principal component analysis. Any questions so far? And now we come into the real thing. And remember that behind the scenes, which I've taught you already, theoretically. Yes, Rama.
Yes, sir. Apologies for taking us back a bit. So when you go to the correlation metrics, the output, yes, please. The values at the far right and the -1.0 right down to
range.
Okay. So please arrange for what? Is it for the p value?
Ranges between -1 at the bottom to +1 at the top. Remember, the other bit here is the ruler, so you don't use that. But this value is +1. Then when it comes down, you see that there is a proper -1 in addition to the ruler.
Okay. So please, is it the range for the p values or for
No, it's a range for the correlation coefficient.
Okay.
As for the p values, it can be any number from 0 to infinity.
Okay, thank you, sir.
Yeah. Actually, sorry, it's from 0 to 100%. The p-value. The p-value is from 0 to 100%. But then this one is from -1 to +1. All right. So now let's do PCA proper. I've done this write-up so much that it should be self-explanatory. So how do you do a PCA here? Remember, behind the scenes, the CPA is using the similar value decomposition. But we are not going to talk about it today. I told you that all of them will make sense, but you're not going to talk. So the first thing you're going to do is that you're going to define the number of principal components to generate. Remember, we have how many variables? 7. How many do we want? We don't know. So you would want this thing to tell you how many principal components should I use. So you want it, first of all, to generate them, all of them, and let's see. So and remember, you are working on the scale data. This one, the one you just have above here. That's what you're going to use, not the original data. So this is on the standardized data. Then the PCA will indicate n component equals to n with a random state. Now, the n components will tell the system to compute all the possible components. As for the random state, what it will do is that it will ensure that you are able to reproduce in case the PCA needs any randomness. So, and we set it always to 1. It doesn't change. In case that you need some randomization, then it will do that randomization automatically for you. So this is that. So we don't know the value of how many principal components we are going to have. So we just use n, okay, to represent that number of principal components. Now the n here could be anything. Then you set up a data, this time called data PCA1. And what this one will do is that it's going to find the covariance matrix. It's going to find the eigenvalues, the eigenvectors, the direction of the maximum variance. In other words, it's going to do everything we know about singular value decomposition. And it's going to do that on the transformed data, the standardized data. And then the most important thing, it will calculate the percentage of variance explained by each principal component. You calculate the percentage of variance explained by each principal component. So look at this thing. It says X explained variance equals to principal component analysis. Give me the explained variance ratio. Now, what does that mean? And I'll explain it to you when we show you the graph. So first you run this, okay? And then you visualize the result. You visualize the result of the explained variance by each individual component. Now, how many principal components how many variables did you have? How many features did you have? Do you remember? 7, okay? So that's why you see that the x-axis is up to 7, okay? And then, of course, the cumulative explained variance is going to be 100. So the vertical axis is 100. Vertical axis is 100. So that is how it's supposed to be here. Now, the next thing you got to do is calculate, run this command. Just watch this. This puts the size smaller. Okay. It puts the size smaller. And then you have the lines in there. Okay. Now, these are just titles. These are just titles. This last one, they are just titles. And you can see that you have a marker. Now, here I decided to make it a little bit beautiful by indicating that the plot point will have the marker, then the lines will be zigzags, and the colors will be green, and all of that. Now, when you look here, you see that you should run yours and get the same result. Okay. What do you see? the curve will generate an elbow. And the elbow will tell you the number of principal components to select. It must be a reasonable elbow. The components are on the x-axis. When you look at the x-axis, where does the first elbow, proper elbow, okay, you can tell us. Where does the first elbow, proper elbow, okay, Pascal?
Doc, please, 3.
3. It is true. Okay. It appears that there were going to be a curve bend, an elbow at 2, but it wasn't really 2. It eventually happened at 3. Okay. So clearly, you can see that. So what does that mean? It means that out of that 7 variables, we can reduce all of them into 3 variables by combining some of them. And those some of them we are combining are those that are highly correlated with each other. So after performing the principal component, you notice that each component will explain a percentage of the total variability. Okay, we are going to see that very soon. Now that you say 3, you're going to see how much does the component 1 explain, how much does the component 2 explain, how much does the component 3 explain of the data. Of course, which one will take the highest explanation? Which one will take the highest explanation of the variability, of the information in the data? Which of these components, now that we know there are 3, which of them will take the greatest variability? Edward?
Component 1.
Eddie?
Component 1, the very first component.
And which will take the least?
Since we are doing 3, then component 3 will take the least.
Okay, so that is it. Okay, now that explain thing, it tells you the percentage of the variability explained by each component. The whole idea is to find the smallest number of principal components. Because suppose that it has told us that the number of principal components we should use is 7. But then the variables are already 7. So then it becomes useless. Okay? Because the idea is to reduce the dimensions. The dimensions are 7. You want to reduce it. So you can't tell me to still do. So you want the smallest, but that should also explain at least 90% of the information. So the fact that we want smaller number means that it doesn't mean that, oh, because they are small and they are not doing any explanation, and then you still take them. No. This is very, very crucial, because the whole idea of the work is to reduce the dimensionality whilst maintaining or retaining the most information. Okay, so now we know we have to do 3. Let's see the principal components. Which ones are they? And then how many percentage are they doing? So run this. First of all, this command, just read the information around it. You see that it's fairly, fairly simple. What this command is doing is that it tells you that the 3 that you selected, how many percentage of the information they are containing. How many? And in this case, you want to confirm whether the 3 actually explain at least 90% of the information. So it tells you the information here. The number of principal components that explains at least 90% of the information is what? Is 3. So it's confirming that. So from the 7 original variables, okay, we have reduced the features, the variables, using PCA to 3. And these 3 explain more than 90% of the original variability in the data, of the original information content. They can explain it. So in other words, you don't need all the 3 or all the 7. All the 3 are enough. Okay, that is what it means. Secondly, what it means is that 57% of the information in the dimensionality has been reduced. So we've been able to reduce 57%. Now, how do we get a 57? It is 7 minus 3 divided by the overall 7 multiplied by 100. Okay. And that 10% that we couldn't do, okay, that 10% is not captured by the first 3 components. But that's okay, because at least we are capturing at least 90% of the information. So let's see those principal components. and which variables combine to make up those principal components. Okay, this is the most important thing in the work. Look here. You can now run this command. This command is self-explanatory. Okay, so you just want to create a data frame that matches the component with the variables. Okay, the variables of the scaled data. Remember, this is for the scaled data, not for the original, the scaled data. But that's okay because that's all we dealt. So once you run it, and then of course you want to transpose the entire result, the entire matrix, so that you can see the principal component at the top. Once you run it, you get this information. Guys, you just don't know how beautiful this thing is as far as I'm concerned. So what it means is that the principal component 1, these are the variables that load. The information you're seeing here are known as loading factors. Loading factors, loading factors, loading factors, loading factors. And let me tell you how you will know which variables are matching towards principal component 1 and which variables are matching towards principal component 2. Guys, remember this. In an exam, you should be able to use this to answer a lot of questions. Remember that a variable cannot match onto principal component 1, and that same variable also match towards principal component 2. Debbie. So once the variable matches towards a particular principal component, it must not be used for the other ones, which means that it must load more towards PC1 than PC2 and PC3 for that variable to be said to be associated with PC1. Please, are you with me? Are you with me? I want to hear your voice. Are you with me what I just said?
Yes, Doc.
Fantastic.
Yes,
Yes,
Doc.
Doc.
Doc, can you please say that again?
Okay, so as an example, whether it's positive or negative doesn't matter. Take, for example, weight. Okay, weight has got some loading factors or some weight associated with principal component 1, 2, and 3. The weight for principal component 1 are underweight. The weight, or let's say the importance that the car weight brings to principal component 1 is 0.41. The importance the car weight brings to principal component 2 is 0.22. And the weight that the importance the car weight brings to principal component 3 is 0.2. You would take the one that is highest in absolute terms for that particular principal component to use that. So when you look at it, which of them does weight, or which of them would take the weight coefficient? Is it PC1, PC2, PC3? Which of them would take
PC1?
PC1? Why? Why?
Because it has the largest weight.
Good. What about model year? Which variable would take that? Which component would take that?
PC2.
PC2.
What about displacement?
Doc, PC1.
PC1. So you can see that if we go to PC1, we can get all the variables that match. So for PC1, which variables will all be taking PC1? Mention all the variables. And of course, I'm sure you are mentioning them relative to the other ones. So the first variable will be what?
Cylinders.
The next one. But before cylinders.
MPG. Cylinders, displacement, horsepower, and it ends at weight.
Yeah, but MPG has a challenge there, isn't it? So normally you check this one too against the correlation matrix you had. Okay, so let's say, for example, you're talking about MPG, and then MPG, and once you take MPG and you take cylinders, then the two of them must be highly correlated with each other. So you go and check whether looking at a correlation, MPG, this is MPG, okay, and then you look at cylinders, this is cylinders. You see, they are negatively correlated with each other. That's okay. Let's see whether the others are negatively correlated. This is before you even add MPG. So you also took cylinders, right? So let's go and check cylinders and MPG. Okay. This is cylinder and MPG. Oh, what is that? This is cylinder, negative. What was the first one we dealt with? We chose MPG, right? Okay. So cylinder and MPG, there is a negative 78% correlation. What was the other variable you selected?
Oh, the cylinder.
Yeah, we've done the cylinder. What was the other variable you selected?
Displacement.
Displacement. Very good. So we go to check displacement. Is that also negatively highly correlated with MPG? No. You see it? But then take cylinder and displacement. They are highly correlated positively, isn't it?
Yes, sir.
Look at it. Cylinder and displacement. So the fact that MPG has got a negative value doesn't make it tease itself with these values. And I know that possibly because I said that the negativity doesn't matter, but it does. You got to juxtapose all of this relative to the correlation matrix. Juxtapose all of that. So the cylinder will move along with displacement. All right. So the two of them are together there. Which other variable can join? Horsepower is also there. Okay. Which other variable? Weight. So cylinder, displacement, horsepower, weight. Okay. Watch their correlations. Watch their correlation. Cylinder. Cylinder, displacement. You see, they're all high, isn't it? Cylinder, displacement, horsepower, and weight. Cylinder is highly positively correlated with all of them. Look at displacement and cylinder. Okay, displacement and horsepower, displacement and weight. They are also all above what? 90%. Are you guys with me?
Yes,
look at horsepower and cylinder, horsepower and displacement, and then horsepower and weight. Okay, all above 80%. So that shows that these will make up truly principal component one. Now, of course, we'll use a graph to confirm all of this. So that is what gives you the loadings, because you're able to see that these four variables load very well, which means that when we come to principal component 2 and 3, those ones will not be used. So we are left with what? Principal component 2. Okay. The variables that we have to deal with are MPG. Okay. MPG. But let's leave that one for now. Let's go to, because these first four have been taken, let's go to acceleration and model year. Which variable will take, which principal component will take acceleration? Remember, PC1 is not taking it. It's PC3, isn't it?
PC3. Yes,
very good. And which one is taking model year? PC2.
PC2.
Good. Now, between PC2 and PC3, relative to acceleration and model, which of them do you think is going to take MPG? I know which one, but I want to see whether you know. Which of the PC2 and PC3, which one will take MPG?
PC2.
Perfect. Hey, I say it is PC2. And why? Why did you say PC2?
Because it's positively correlated.
No, you haven't seen the correlation yet. What you are seeing is loading. It's not a correlation. It's a loading between the variable and the PC. So if you want to know, because remember, the moment you take it to PC2, it means that it must have something together with what? Model year, isn't it? It must have some relationship with model year because model year has been taken by PC2. So if you're going to say MPG is also for PC2, then you got to find a correlation between MPG and model year. That's it. So you go up there and go and check MPG and model year. You see the correlation is what? 58%. And now check MPG and the last one. Was it acceleration? Yes. MPG and acceleration is what? 42. So MPG is more correlated with model year than it is correlated with acceleration. And therefore, makes sense to, because already PC2 has taken model year, then MPG would take PC2 as well, because when you check the correlation above, and then PC3 will only have what? Acceleration. Hallelujah. So these ones are powerful. Of course, this is the same thing that is here. Okay, it's the same thing that I've generated here. So let's write. So if I want to write the principal component 1, I will say that principal component 1, okay, is equal to 0.42 cylinders. That's what it means, because it took cylinders. 0.42 cylinders. And if it is minus or plus, you indicate it. Okay, plus point. I'm writing something called principal component equation, the equation for principal component 1. 0.43 what? Who can tell me? 0.43 what?
Displacement.
Displacement. Very good. Then the next one will be what? Point what?
42 horsepower.
42 horsepower.
42 horsepower.
And then plus 0.41 weight.
Exactly. 0.4. You'll be writing some of these things. 0.41 weight. Should we continue, or that's all?
Doc, that's all.
That's all. So this becomes the equation for principal component 1. Okay. So that is it. By looking at this, you know which one is loading towards the other one. So when you come here, each principal component is a linear combination of the original. So for example, we can write principal component 1 as 0.4. Okay, so this one, we added 0.4 mpg. That's interesting. So it's good. It's good. Let's see why that is so. Let's check the correlation. Okay, so the correlation was 0.6, 0.78. Okay, 0.78. And when you check these values, okay, which means that even though I didn't want to use that, okay, I didn't want to use that because of it still comes back to the point that you should ignore the absolute value. Sorry, you should use the absolute value. Okay. But if you have to use the absolute value, then this one will go with that. But of course, it must match with the correlation up there. In fact, when you go up here, just to let you know, when you go up here, this one shows a high negative correlation and with MPG. But you can see that the others are also showing high negative correlation with MPG. Okay, so look at this. They are all negative, 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 and they are all part of the family of the yellow section, as you can see here. But when it comes to MPG, they are all black with it, which is okay. So MPG should be correlated with them, just that it should be negatively correlated with them. And then when you use this one, you can see that the principal component 1 is highest in absolute terms. And this. So if you have to start, then this is going to be minus 0.40 mpg before the one we wrote. Please, are you guys with me? If you don't get it, let me know. And then I can explain it again.
No, please, could you go over this?
Okay. So what I'm saying is that when you're looking for which principal component gel, okay, which ones are gelling with this, you take the one with absolute value. Okay, so the one with absolute value will be MPG, cylinders, 0.43, 0.42, and then 0.41. Okay. They are the highest for PC1 than all the rest. And then when you go and check the correlation will still be high in absolute terms as well. The correlation will still be high in absolute terms. So when you look at all these yellow guys, they are all having a high correlation in absolute terms. And also this one too is having a high correlation. But just that it is negative, but in absolute terms, it's also having a high correlation. So MPG is grouped with these guys together. MPG is together with these guys. And so when you're writing the PC1 equation, the linear combination of all original variables, you would take the MPG plus that of cylinder plus displacement plus horsepower plus weight, because they all share a high correlation, absolute terms. And when you go down to the PC loadings, okay, when you go down here, you notice also that in absolute terms, they take the highest values for PC1. Does that make sense now?
Yes, Doc. Thank you.
Yes, Doc.
Now, when you take this second one, okay, let's take, for example. So because of that, what that means is that when you come here, okay, in absolute term, PC3 would take this point. Oh, sorry, this one has taken it already. MPG has taken it already. So nobody else would take MPG. Then when you come here, acceleration would take 0.89, and then model year would take this middle one. So PC2 would take model year, and acceleration, PC3 would take acceleration. Okay. We've already done those ones. The only thing is that when one takes the other, no other principal component will take it. Anyway, so the principal component one will be this. Let me just bold in it slightly. Okay. So that will be principal component one. And this would be the equation for that principal component. So this is it. So you see that it tells you the weight attached to that particular variable in helping in the combination process. So the first principal component measures MPG, cylinder displacement, horsepower, and weight. It's associated with a high score of all these variables except MPG, as these variables have positive 1. PC1 is associated with low values for MPG. It seems to capture attributes that generally defines cars. And this is just a way, and I will show you something very soon. That will define cars with heavy engines. You just check it. All of them are kind of a measure of the engines. Not all of them, though. Most of them, okay, unlike weight. Heavy engines with high number of cylinders, okay, with high number of displacement, high number of horsepower, and higher weight. And a result of heavy engines such as cars will have a low mileage. And so no wonder that the mileage was negative in that case. So in other words, cars with those higher information of what I've highlighted here, those cars will have a lower miles per gallon with what is on the left. Now, the second principal component is a measure of model year, just as we said. Okay. The second principal component, I'm sure you guys remember this. Okay, it's associated with a very low value for the model year. And then finally, the third principal component measures acceleration. So you can use that to know that, okay, so now when I'm combining them, I'll combine MPG, cylinders, displacement, horsepower, weight all together. Then I'll combine acceleration on its own and then take model year also on its own. So the 90% probably didn't even consider acceleration and model year. So the rest of the information is enough than acceleration and model year, basically. Let's put everything in graph, then you can see. But this graph, we can't draw it 3. We are taking just 2 principal components. So we're going to draw a graph between PC1 and PC2. Remember, PC1 explains the highest information. PC2 explains the next highest. So this is PC2, this is PT1. We're just doing a scatter plot, okay, where you plot all the variables between these 2 principal components. And how do you do that? You just run this command, okay? Take PC1, the data set, okay? And then that's the 0. And then for the PC2, which is the data set. Okay, no, this one is also PC2. That's a y-axis. The x-axis is a PC1. So this is principal component 1 for the x-axis, and principal component 2 for the y-axis. And these are the labels for each one of them. When you run it, you get this very score that you are seeing. Now, the score doesn't tell you much. I mean, this graph doesn't tell you much because you don't know the separation. Yes, Pascal.
Doc, please, is there any peculiar reason why we chose to give principal component 1 the x-axis and component 2 the y-axis?
Is there any particular reason why? No, there's no particular reason why. What,
Okay.
the graph doesn't matter. When you rotate the graph, they will rotate, but you still know the relationship.
Okay,
Yeah.
sure. Thank you.
So suppose I say there's a negative relationship between price and quantity. If you draw it in the way, y comes to the price comes to the y-axis, the quantity goes to the x-axis. But when you bring the quantity to the x-axis and y, it will still show a negative relationship. But it doesn't tell us the groupings, eh? You can't fish out the groupings here. So here, let's put some colors in there. Let's separate them according to cylinders. See, we're going to add something called hue to the scatter plot to create a scatter plot for just the first 2 principal components, but separated by cylinders. This is beautiful. This is the first one. I didn't like this, but at least it gives you some groups. It tells you that in terms of cylinders, most of the, look at number 8, most of the 8-cylinder cars are more towards the right-hand side here. And then there are some overlaps. For example, the 3-cylinder cars are on the left here, but if you look here, there are some other deep ones, like 5 and 4 inside it. So this one didn't give us a proper coloring, So I decided to change. You can run that, by the way, to change it to this. And this one gave a proper color. What do you see here? We're just trying to scatter plot the data now between the 2 principal components, okay, as far as the observations are concerned, in terms of cylinders. Okay, so this is like a mixture of k-means. So look at, first of all, the 3-cylinder cars. They are kind of scattered. There are a few 3-cylinder cars among 4-cylinder cars. But do you realize that there are many 4-cylinder cars grouped together? Do you see that? Many 4-cylinder cars, that's a blue, are grouped together. And some people don't know where they should belong to, like the 3-cylinder cars and the 5-cylinder cars. They don't know where they should belong to. So the 3 and 5-cylinder cars have grouped themselves. Some of them have positioned themselves among the 4-cylinder cars. And then, of course, the 6-cylinder cars, a couple of them have also eaten themselves into the 8-cylinder cars. But what does this tell us? The first point is that, and this is a key point here. We can see that there are 3 groups. There are 3 main groups of cylinder cars. But when you look at the actual cylinders, okay, the number of cylinder cars were not just 3. There were quite many. There were quite 8, different cylinder cars. But if you can remember the numbers I showed, let's go back. Then you see it. Okay, let's just go back here. Where is it that I showed the cylinder? Here. So these are the number of cylinders. So we have 4-cylinder cars, 8-cylinder cars, 6-cylinder cars, 3-cylinder cars, 5. So the major one is 4. And then you have 8. Then you have 6. Okay. But the 3 and 5 combined are just 7. But we can now see that among the cylinders, just looking at this graph, with the help of our PCA, we can now have only 3-cylinder cars. Okay, let me conclude with this. So the point is this. We've already finished, though. I'm just adding something related to grouping here. The point is that, and it's written here, that we have one group which are 3, 4, 5-cylinder cars. They are the ones on the far left. Then in the middle, you have 6-cylinder cars. Then on the far right, you have 8-cylinder cars. Okay. So what this means is that we are able to know which cylinder cars are grouped together. And of course, you will agree with me that the the 3 and the 5 cylinder cars, you agree with me that they have no choice than to join the 4 cylinder cars because they are closer to the 4 cylinder cars, okay, than they are to the other cylinder cars. If you look carefully at the 5 cylinder cars, it was a bit closer also to the 6 cylinder cars, more than the 3 is closer to the 6 cylinder cars. So clearly, you are able to use this principal component to also even subcategorize the data into which groups, a particular data point will be relative to the principal component. But hey, this group analysis is not the best. Why? Because you can see that the red spot have mixed with the blue spot. So it's not perfect. But the most important one for principal component is this. We have been able to now compress the entire 7 variables to 3 variables. Maybe we need to get a name for the PC1. Remember, this is made up of NPG, cylinders, displacement, horsepower, and weight. We need to get a name for it. What name can we get for it? And then PC2. What name can we get for it? I tried to come out with some names. So watch it. Engine-related cars. Okay, so you can put all of them together and call them engine-related cars. Engine-related. Okay, engine-related cars.
Yeah.
I'm trying to combine the other one, but the other one, they are only one. PC1 matches with variable. Sorry, PC2 matches with variable.
Model year.
Model year. So let's get the name. It's still going to be model year because it's only 2 variables there. And then PC3 matches with acceleration. So we can group the first ones as engine related, then accelerated, because that acceleration has to do with engine. I think it does, Joanna. I don't know. But that's a key point. You can find a beautiful name for them. Very good. Any question on this? We have a second data. I will not show all of the second data. I've just written the same thing here for that. But I want you to look at them. But I'm going to start and show you some few key points. So this is a second data. And this second data is the educational data set in the US. It's a very simple data set. Look at the columns. You have the names of the various universities and colleges in the US. You have the number of applications that each university receives. Whether the number of applications were accepted or not. Number of new students enrolled, that is enrolled. The percentage of new students from the top 10% of higher schools. The percentage of new students from the top 25%. Number of full-time undergraduates. Number of part-time undergraduates. The cost of room and board. Estimated books for students. Estimated personal spending. Percentage of PhD faculties with PhD. Or faculties with PhD. Percentage of faculties with terminal degree. S and F ratio, that is the student-faculty ratio. Percentage of alumni who donate. The instructional expenditure per student. And finally, the graduation rate. Are people really graduating? So you import all the distance, and this is the data set. That's the data set you see there. Let's try and fill some few things in the data set. We've already known all of this. You can check the mean, and these are just the first 5 variables. And you see that all of them are numbers. If you check the information, check it carefully. Names are objects. That's what we know. And then there is no object again. Okay? So it means that we don't need to do any, median adjustment or mean adjustment or missing value, nothing, everything. The 77 observations are all sorted. All the columns are non-null, so no missing values. And then you can now prepare the data and exploit the data. Descriptive statistics are all here. Everything here, on average, you can see that 3,000 applications are received in the university. You see that from this number, the mean application. 3,000 applications are received. On average, that is per one university. That's the number of applications received. Out of which 2,000 applications are accepted by the university. Okay. So the 2,000 here is those that are accepted. The second one. It's approximately 2,000, but it's actually 2,018. So it's finding some few information. And then 780 new students get enrolled. That is this one, enrollment. 730 new students get enrolled. So you can find a lot of other information about it. Now, there's something about these particular variables, and it's important you note. See, if you check the PhD and grad rate variable, they are supposed to have a maximum value of 100. But some of them, when you go to the columns, some of them don't have 100. They have more than 100. Let's see. So I call for the data and I said, I want you to tell me the PhD column and the graduation rate column. Tell me which variables are more than 100. Okay. Okay, I've not loaded the data. But if you have, you'll notice it. Variables are 100. And you'll be able to know which variables are 100. So let's run this. So you see that the row number 95 and 582, the row number 95, check the graduate rate. Okay. It has a number 118. That's not good because the maximum value or percentage you can get is 100. And if you look at row number 582, okay, look at the PhD column. The PhD value is 103%. Okay. That doesn't make sense. Now, by the way, just so you know, what do you mean by the PhD? So when you check the data here, the PhD talks about the percentage of faculties with PhD. And you say that that particular university, okay, the number of faculties with PhD is 103%. So these are wrong information that have been entered. You got to set it up. So force everything to be a maximum of 100. How do you do that? You just run this one, say that the data here for this observation should be 100. The data here for this observation too should be 100. Maximum 100. So that we don't have any wahala. Okay, we are done. Now you can check the distribution. We did that with the other ones, so I won't go too much. So this is a distribution. Some of them are right tail, some of them are left tail. Some of them are outliers, some of them are normal, some of them are non-normal. Okay, so you get all of this. And here's a clue here. The distribution plot shows that applications, whether or not a student is accepted, enrollment, top 10%, blah, 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 all of these are highly right skewed. They are all highly right skewed. But let's just take, for example, application and then acceptance. Look at it. Okay. Let's explain to you. So look at these two alone. This is application. And you can see that it's very, very right skewed. Right skewed means where there is flat, bars, where there's a lot of flat bars. So the flat bars, are they on the right or on the left? If they're on the right, then that is right skewed. If they're on the left, that is left skewed. And so this first to accept and then apps, they are all right skewed. And then you can now find some other information. Once again, let's look at the correlation matrix. So again, this one is a lot of data. So you can see the correlation matrix is many. But hey, it doesn't matter. You know what it is. Okay. The red ones will give you a clue of higher correlations. in positive terms. Okay. Higher correlations. And then very deep blue, like this 55, will give you the lowest, the lowest correlation in negative terms. Well, let's put it, the highest correlation in negative terms. Yeah. Or the more negative correlation. So you are able to use this to get a feel of which variables are likely to match each other. And this is it. You can conclude that we can see high correlation among the following variables: apps and accept, apps and blah, apps and undergraduate, apps and row, up. You can find each one of them. And those that have negative. Done. You can now scale the data. Now we know what scaling is. I brought all of them here. You scale the data, you show the head of the scale, and all the values are between -1 and +2, or -2 and +2. Who is not clear, let me know. Now we're ready to do the PCA. Guys, watch this. This is interesting. So you run the PCA, and then you run the explain variability. Just like the other one, how many variables do you think should be selected for the principal component? How many? In fact, this thing is too big. So let me make this one 5. I hope it works. Yeah, the reason why it doesn't work is because I've not run the others. Let me go and quickly run the others. Okay, so this is the correlation. And then I didn't do the scaling, so let's do the scaling and show the scaling. And then run the principal component. And now let's see the result. So now it's made it a bit smaller. Okay. Now this is a bit tricky. So how many principal components should you select? Or do you think you should select? Right there. How many principal components do you think we should select? But there's a reason why. There's something also why you should do something why. So be careful with your answer. When I said that, now somebody has reduced the hand now. I mean, okay, let's start. It looks like it's what? It looks like the number of PCAs is what?
It looks like it is 2.
No, 2.
Yeah. But why is it not 2? I mean, if you can tell me why it cannot be 2, I will applaud you. Restford.
Doc, I think because we have a lot of variables to work with, so it's very unlikely that the principal components will be 2. It's likely to be more than 2.
Not exactly. Not exactly at all. Yeah, but not exactly. There is a reason. It's there in the graph. You must have a critical eye to look at it.
Hello, Doc. Sorry, I'm unable to raise my hand. Okay. So in my opinion, it still continues curving out even after 2. So
It's a
probably that's
curving
why it's
out. I need to understand what you mean by that.
it's still a bit still going. The curve is still quite sharp after 2.
What do you mean by quite sharp?
The angle of the curve.
It takes a lot of components before the bend, the turning that it did at 2. It takes a longer time for that turning to turn again. Do you see that? Let me repeat. It takes a longer number of components before there is a next turn after 2. takes a longer number. I mean, it can be a straight line. Do you see that from 2, it can be a straight line up to where? It can be a straight line up to where?
Up to 6.
Exactly, up to 6. It can be a straight line up to 6. So if you tell me that it's 2, okay, there are a lot of other components there before the next bend. But if after 2, it now does another turning at 4, then it means that what we had was truly 2. But it continues after 4. It continues, until after, it continues even after 5, until after 6, before the turning begins. Yeah, I mean, the slight next turn. That is why it cannot be 2. This is a clue. This is a clue. This is a clue. Therefore, the number of components has to be 4. And please don't worry, because there's always a way. In your thesis, for example, in your long essay, there's always a way to check. But I'm just giving you the interpretation. Okay. So, how do you check? How do you check? This is how you check. Okay, I've given you this command in the previous one before. So you want to find out the percentage number of components that are needed to be more, for the number of components to be more than 70%. I think 70%, 70%. Okay. So these are 17 variables, by the way. So when you now indicate, I want you to tell me that how many components would we have more than 70%? In fact, let me show you something. This is 4 components. Let me change this to 9. 90. So you see the 90 says that we should have 9 components. Do you see that? Are you guys with me?
Yes, Doc.
90, if you say that, I want you to tell me in terms of the variance, okay, how many components will I get if I want the variance to explain at least 90%? It's going to tell me that I need 9, which is cool, but then that is too much. So to be able to confirm that the number of components you need should not be more than 9, that would depend on the percentage variability. And guys, I won't lie to you, 90 is not automatic. Sometimes some literature will even say that use 70. Some will say use 75. Some will say use 80. And so when we use a 70, it helps to reduce the number of components to 4. But that is because between that variable, the thing was still steep. It was not really curving until potentially after 6, where it even curves a little. And when it curves a little after 6, and then it went to 7, do you realize that it kept going like that? So we can now say that the number of components to select is going to be 4. Of course. So the reason why we are selecting the 4 is both graphically as well as using the number of percentage that is explained by the, by the whatever principal component that you want to have. So if you have a particular number of principal component, you want to know, they explain how many percent of the data set, and you can get. Okay, so we have reduced the 17 variables to 4 variables. So about 76% reduction in the dimensionality, okay, with a loss of 30%. 30% is because we chose a 70%. So the information we cannot explain is 30%. So now how many pieces are we looking for? 4. So we run the pieces and then we now obtain our 4. And now you can see that these are a lot of variables. So if you want to write your principal component 1, or the linear combination of the original variable, Okay, the component with the most linear combination, or with the linear combination. If you want to write a principal component 1, then you can easily do that here. Let's just take the first and the last one and see. Okay, so the first and the last one, they will go to which principal component? The applications. Applications, university applications. They'll go to which principal component? 2.
Component 2.
2. And then the last one will go to a the last one.
Doc, please, 4.
Exactly. Okay. So now you should learn how to do. Of course, you write the equations just as you did for the first principal component. It has a lot of the variables. You write that, and then what is the practical implications of this? Well, the first 2 principal components will tell you 58% of the data. So picking up a considerable amount of variation is better. And then you will also notice that what value of importance is high or low may vary from case to case. So it's important that you recognize the problem at hand and deal with the problem. So these are the conclusions that you can see. I did a completed one, a complete one. This is a graph, okay? But this graph didn't tell me the group. So guys, I have this one for you to look at on your spare time. This is the same thing for this principal component. I created a principal component for the first 2 out of the 4. And then I use k-means to group them and then look at how they look in the PC scatter plot. And this is what you get. Okay. So when you look at this, and I decided to just please go through it. Let clustering do the work for me. Clustering cluster a thing into 4 groups. And then it tells you which particular group is doing well. I mean, you will know the groups that are high, because if you look at PC1 and then PC2, okay? If you look at the coefficients are the axis. Yeah, the axis here. So the red guys, I don't know what names they are because it just was just created. The red guys are having high in both angles. Okay, they're having high both on the PC1 and PC2. The green guys are having high on PC0. Then the blue are having high on the PC2. And then on and on and on like that. So please familiarize yourself with this more because I didn't go through that in detail. And principal components is just basically to reduce the dimension. Makes sense. So don't just reduce, but when you reduce, check the percentage to be sure that you are getting a lot of percentage so that you don't lose information. Benjamin, that brings us to the end of the entire caboodle. If you have a question, feel free and ask your questions.